We are now here. We have iterated over the modules and all the conf classes. You can see that the last value for M is conf2d 1024 and 255. This corresponds to the last layer right here, where we have 1024, and then the 255 comes from the fact that we have 80 classes plus 5, 85 times 3, 255. So essentially, we have iterated over the whole neural net, and now we're going to print the model information here to the terminal. So self.info is essentially calling this function right here. So we're going to call self.info, and we'll jump right here. And now we're going to call model.info, was inherited here at the top from utils.torch_utils. Now we're inside model info within torch utils. So model is detection model. We know that detection model inherits from NN module. Base model and base model inherit from NN module. And NN module has some properties. One of them is parameters, and another one is name parameters. So essentially, in the module class, we can call specific properties. For example, the parameters one. So we can call the parameters of the model and iterate over every tensor. We can also call, in a similar way, the named underscore parameters, which will give us both the name as well as a parameter. So in our case, we're going to call parameters from torch utils. So for every parameter, we're going to call it, and we're going to add the number of parameters. Num returns the total number of elements within a tensor. So for example, here, if we have a tensor of 4 by 4, we will have 16 parameters. We're going to calculate the parameters for each tensor, and then add them and store them in n_p for number of parameters. We can also see that in our YOLO environment. So if we haven't already, we can run this code right here, and then open this section, model summary. Here, unlike the previous video where we did it step by step, here I'm just going to, with one line of code, fuse the layers. And we can actually print our model. We can see that our conf and batch norm have been fused. So we have conf and then activation. And then as we saw in VS Code, we're going to call model.parameters. I'm going to print the tensor shape and the number of parameters. If we need to calculate gradients or not, it's going to be false because we're doing inference and not training. And then here, I'm just going to print the first 4 layers that have parameters. So you'll notice that we won't see the activations because the activation functions do not have parameters, but the convolutional nets, both the weights and the bias terms, will be printed here. So we should expect to see only 4, the convolution, both the weight and the bias, as well as the convolution of the second layer, both the weight and the bias term. When I run that, we get the shape of the convolutional weights for the first layer and the total number of parameters. This is the result of multiplying 64 by 3 by 6 by 6. These tensors have required gradients set to false. We see the shape of the conf bias parameters, 64. And then the second layer has conf weights of shape 128 by 64 by 3 by 3. When you multiply all those numbers, you get this number. In a similar fashion, we have 128 bias values for the second layer. We can also print the name of those parameters. We can see that we have both the weights for the first index 0 as well as the second index 1 layer. So coming back here in VS Code, you see that we just stepped over the conf weights for the first layer. When I run it again, the parameters of this first layer are 64 by 3 by 6 by 6. You can also see that requires grad is set to false. When we run it again, we get 64. Again, this corresponds to the bias term. When we run it again, that's the 73,000 that we saw, as well as 128 for the bias term, and so forth. So when we run this for all the layers that have parameters and then add all those parameters, we obtain a total value of 46 million parameters. Given that all of them have the requires grad set to false, NG will be 0, as you can see here. We have verbose set to false, so we'll step over this. Here, we're going to get the parameters of the first layer with parameters, essentially the weights of the first layer. That is P. We can see that is the 64 by 3 by 6 by 6. Here, we're calculating the max between model.stride or 32. Model.stride. So the maximum, 32. If we have the attribute model.stride, which we can see here, we do. So the output is going to be 32. And then here, we're calculating an empty tensor with shape 1. P has shape 64 by 3 by 6 by 6. So we're getting the index 1, which is 3. So this will be 1 by 3 by 32 by 32. And towards that empty creates an initialized tensor, as you can see here as well. This line of code calculates the number of giga floating point operations per second required for a forward pass and a backward pass of the neural network. This line uses this library, makes a deep copy of the model to avoid modifying the original one. We will feed in a dummy input of an initialized data. In this case, 1 by 3 by 32 by 32. It will be one step of the neural network. We will return the first input. We will divide it by 10 to the power of 9, or 1 billion, to have it in gigaflops instead of flops. And then we'll multiply by 2 to estimate the gigaflops, or the computational workload of training and running a model in both the forward and the backward pass. So we run this, and our gigaflops are 0.27. Here, our image is 640, as defined here at the top. We're just going to convert it to a 640 by 640 list. And then here, we're going to calculate the flops for a 640 by 640 image. Here, we calculated the gigaflops for one step, but given that our image is 640 by 640, and we have a stride of 32, we're going to be performing 20 operations on both the height dimension as well as the horizontal dimension. So our gigaflops for one step will be multiplied by 20 to do the forward and backward pass vertically, as well as the forward and backward pass horizontally. So when we run that, we obtain 109, which is 0.27 times 20 times 20. Now here, if we have the attribute YAML file model, YAML file, replace YOLOv5 for uppercase YOLOv5 and save it in name, right here. And then here, we're going to print to the terminal this string containing the name, the summary of all the modules or layers, the number of parameters, and the number of parameters that require gradients, 0 in our case, as well as here, the number of gigaflops. So when we run that, we will see it here in the terminal. And now we return to where we call it from, model info, as well as where we call it here inside Fuse. And now we return self, and we're back to experimental.py where we did this function. And now we return it to where we call it from.